I don't know. I feel like everything.
Okay, we're gonna get started. So we're finishing up this discussion of vorticity, and homeworks are, they've been a little weird. We're gonna try and get back to doing one homework per week. That we're gonna be doing Monday. You should have a new one. Continues the work on 4 and a little bit on 6. We're gonna try and weave together some of the computational projects and the using um, of the Navier-Stokes equation and the energy equation and things like that. Okay. You did a problem where you modeled a fluid velocity at the top of the sun for different velocity flows. Did you do that? Yeah, you did. You're supposed to have done that, right? Okay. So here's what it looks like. This is the surface of the sun. These are plasma flows coming off of it. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 Earths tall. They're big. We're going to talk a little bit today about some similarity solutions, maybe just like very, very briefly before we jump into waves. But we're a little behind. So I think, going to waves and going to how we can break down the momentum equation so that we can use it in specific contexts is where I want to end up. So I'm just going to start here. Okay. And then we're going to actually move away from this almost right away. Okay. So this is now all of the equations together. What are they? Okay, first one. Mass what? Mass conservation mass. Yeah, we just call this the vorticity equation. If you wanted to, if you really felt so inclined, you could look at the left-hand side here. This is all the DDTs. So you could call this conservation of vorticity, but you don't necessarily have to, and we don't necessarily call it that in class. Okay, I'm going to assume that you know all these terms by now. So let's just talk about the last one. What is the last equation, and when can you use it?
The first part has to do with I think the vorticity stream function. You said it was like dragging the vortex line. Just stop on it.
So what do you mean the first part? This
Term.
piece, this piece, or this piece?
Oh, I guess the middle.
Okay, so this term here is what?
Vorticity stream function. Well, it's dragging the vortex line, so.
Dragging the vortex line, that's correct. Where?
Last one has a diffusion operator, first name.
Right, so what does that mean? Diffusion operator means it is the diffusion of what fluid? What part of the fluid? What are we talking about with this equation? We're talking about here, how do we generate vorticity? And there's 2 ways to generate vorticity. The first one you said was?
Dragging vortex line.
Well, in particular, tilting,
Right.
right? By tilting it with the flow, you can generate vorticity. And this one here. That's from. What we have here, this whole equation is talking about the vorticity. This one here generates vorticity by the tilting of vortex line with respect to the flow. And this one here does what?
Like, reading it, I'm thinking like accelerating the diffusion going on, but like physically I can't. do it.
Yeah, so you're using some of the right words there. Acceleration's not necessary. If we drop this middle term, don't think about that at all. And just compare this side to this side, then what it says is the total derivative of the vorticity, the way in which vorticity changes, is due to the diffusion of vorticity. So these are two sources of vorticity, or sinks of vorticity, they can go in either direction. And here what this is saying is if I start with a bunch of vorticity piled up, it's going to diffuse outward. So you may have seen this version before when we see it in terms of, say, little d, big temperature, T, little d, T, little d, little t. So the diffusion of temperature with respect to time follows the same format, except for you have big T here instead of omega. And this nu is not the viscosity, but the diffusivity. Right? Okay. So there's two ways then to generate vorticity. And what are they?
Starting with vortex line, or if you have a lot going on the diffusion of.
Okay. We're going to change one word there. It's not dragging the vortex line, but tilting. So if I open this up, right? Let's imagine this is a car and I pop open the hood. What's inside of here is this operator, right? So the big DDT contains inside of it the little partial t and the little partial x operating on this thing omega. So inside of big DDT is the steady and the advective component of omega. So on the left-hand side, I also have two terms. So on the left-hand side, I really have, how does the vorticity change with respect to time? And how is the vorticity advected in the fluid? So the idea of dragging vorticity from one place to the other is actually hidden in the left-hand side of this term, not on the right-hand side. So this is from tilting, this is from diffusion, and then hidden inside of here is the dragging and the time generation, right? Cash money towards the ceiling. Okay. Is this valid at all times? Is this as general as this is? No, that's correct. So when can I use it, Elliot? I basically had two conditions that I needed to satisfy. No, that would be for the Bernoulli equation. No worries. We will use it in the context of boundary conditions, and particularly this is quite helpful to solve on a computer. But we're gonna use two approximations here. One is we're gonna assume that the density depends not on the conditions therein. So we're basically taking something like this, and we're saying the density is constant, or that it's barotropic, I should say, not exactly constant. And then we're also going to say, more importantly, that the viscosity is constant. The viscosity is not varying within the fluid. Okay, and those are our basic two assumptions, and from that you can then simulate water. Right, because you can use this example, the omega, and as we showed at the end of last Monday's, or at the end of Monday's class, you can then solve the stream vorticity formalism. And that is really helpful because rather than trying to solve each component of the velocity, trying to find the pressures, trying to find the gravity, all you have to do is use the boundary conditions, as Elliot mentioned. And the boundary conditions themselves take advantage of that fact that we are dealing with a fluid that exists in a field. Each part of the flow is connected to every other part. And as I make a change somewhere else, it's going to operate on the rest of the fluid. Okay. Okay, so I think that's about as far as I want to go. I mean, you can see this piece here. We talked about it more in detail. That's sort of like, that's what we talked about at the end of class. Talked about it in the context of, let's see, 659, I believe. So this was. This is the stream function, right? So I think we wrote this on the board. We wrote this as the Poisson equation for this del squared del x squared of this thing psi plus del squared del y squared of that thing psi equals minus omega, right? You remember that from Monday? And you can then take advantage of that in order to solve the Navier-Stokes equation using velocity stream. So if you know the stream function, you take the derivative of the stream function, you get the velocities everywhere. And you can do something like find the velocity anywhere by taking something like this of the stream function. So you remember in 2 dimensions that the x component of the velocity, so v of x, is related to the partial of y of psi. And like similarly, the opposite is true. So v of y, u of sometimes called v, is related to the partial of x. So, and that's just in chapter 2, I think, 2 or 3, something like that. That's the first time that we talked about streamlines. So this is the stream function. And the really important thing there is that u, the vector, is the gradient scalar potential, right? Which allows us to take advantage of the fact that when we have del cross u, right, we can use these vector identities because del cross del of something will be 0. So we're going to take advantage of that when we're looking at something like the Navier-Stokes equation, and we want to reduce it to something much more easy to deal with. Okay, so I believe you have a homework right now, which is homework 6 or 7 or something. The homework that will be coming up next is this one, homework 7. That'll be the one after the one that you're just assigned. So this is another computing one. And I believe, if I'm not wrong, let's double check that I did this in the right order. I believe 610 is the driven cavity. Yeah. So you're going to use this streamline velocity function to solve this problem. So if you want to get started on it right away, you're welcome to. I can make this live and just update the numbers, right? Just that you're not doing it 2 weeks after having seen it. Because the thing that matters to me right now, let's see, what did I was going to say here? I think I was going to say the same thing. Oh yeah, we should have spring check-ins pretty soon. Contact me right away. I want to have them next week because we are now going to talk about, oh gosh, come here. It's so hard to see. We're going to talk about these. Okay. Any questions before we move away from have your Stokes equation streamlines, stream functions, check-ins, homeworks weekly.
For Navier-Stokes theorem, is this gonna keep showing up, or is this mainly only involved with vorticity?
So the Navier-Stokes equation is the governing equation for fluid dynamics. What that means is that everything else derives from it. So we will see a lot of modifications. We will see a lot of simplifications, and we'll also see some of the boundaries. So for example, what we're about to talk about are waves. And waves are, of course, where the fluid interacts with something else. So we'll look either at modifications to that, or we'll look at perturbations. So imagine something is completely steady. What happens when there's small perturbation? What do we create, right? So we'll kind of come away from it and we'll go back to it. Away from it, we'll go back to it. Okay, next question. Everyone stoked? What is this? A gnarly wave. What kind of wave? Well, you said wave and I said tide. So which one? Are those the same thing? Okay, all right, we'll get into that. We'll get into that. Tides, they exist on a planet and they even exist in fluids. I don't know if we'll be able to talk about that in detail here. They tend to have a larger wavelength. Tides have a planetary scale wavelength. So we get, say, 2 tides a day. That's due to the moon. These things occur much more frequently, right? These are happening every, how often does a wave come up? Like, maybe like 4 a minute, 5 a minute, something like that. So these will be what are we going to call waves from fluid perspective. Tides are a form of wave, but they're a larger planetary scale wave. Okay. So you see water, you see sand. Anything else that's in this picture that you're missing?
Some shape right there.
What?
So like there's some shape right there above the white.
The white here?
Yeah.
That's the foam, right? Been to the beach recently? You want to go for spring break to do some fluid dynamics study? Yeah, so you go to the beach, and what is it that's missing from the soil that that is there but you can see? I'll give you a hint, it's not under the water. The air. Good. Okay, what causes waves on the ocean? Your instinct will be to say the tide, and that's wrong. So I'll go ahead and cut that one down. Excuse me?
It's involving 2 fluids, the air and the water.
Good. It's involving 2 fluids, the air and the water. And let me ask again, what causes the waves on the ocean? which is called. This is just a simpler four-letter word, the W. Wind, good. Wind causes waves. Right? That's the long and the short of what we're going to talk about today. And really what we're thinking about here is we're going to think about three things interacting together. Okay. So you have the ground. That is a solid. That we do not use fluid dynamics for. Okay. Here's your friend, the beach. This is a fluid. This is called water. This is a fluid. This is called air. So there is a boundary here that we need to consider, the air-water boundary, and there's a boundary here we need to consider, the air surface. Sorry, not the air surface, the water surface boundary. Okay. And what we'll see, of course, is that a couple things are at play when waves are driven by the water. So I'm just going to tell you in words, and then we'll see the mathematics for it. So let's say the air is pressing in towards the land, and it's dragging with it the water. As we drag the water over the surface, the sand below towards the water's interface, right? This is rising. So you're attempting to push this thing uphill, which means that as you press the water together, the shape of anything that's on here, say a wave, is going to change. So if, for example, you have some wave that has a nice crest, maybe it's traveling 1 foot, right? It has a nice wavelength. Now that wavelength, so if it goes up, it has to go down in front of it. It's a wave, right? Okay. Now that piece below is pressing, and it's pressing all that water in front of it. And now you're going to get reflections off of the surface below. You're going to get it back up. And you're going to get braking. And you're going to get the wave to turn over. So in fact, when you go and you look out on a really big ocean on which the surface is not changing very much, you can get these types of waves. They're called rogue waves. They're fucking sick. It's one wave by itself, just living its best life, just headed off in a direction. They're also called solitons. And if you're a boat, they're real scary. Because let's say you're some rickety boat from the 1700s, and you're just headed out there, and all of a sudden a 40-foot wave, just by itself, is just coming right at you. And it'll just hit you and keep going, because it doesn't give a shit, right? Okay. So we want to think about all of this phenomenon. We want to try and understand it to the best of our abilities. We're going to try and couch it a little bit in like our own personal experience, but there is a bit of math here. And in particular, we want to think about how we can use some of the techniques that you're about to see for the rest of your sort of math physics career. Okay. There are 3 primary waves that we are going to interact with today. There are interface waves, there are internal waves, and there are compression waves. So what is an interface wave?
It's just press face
With a different,
with a different surface.
yeah, different surface. So in particular, interface waves occur here at the interface of 2 immiscible media. Okay, they don't happen here. So for example, water and surface interaction will not lead to a wave because generally speaking, the water cannot make the ground undulate, right? So that's an interface wave. What's an internal wave? Within the water. Very good. So if I were to draw, and I'm going to give away some of this, let's draw a couple different examples here. Let's imagine this is my air at the top. Okay, and this is my water on the bottom. So the interface wave might look like that. Okay. And maybe the sea surface raises up here. And when it raises up here, this one goes down a little bit. And so you can imagine those two going up and down like this, sort of like a pendulum, right? And of course, just above that, the air doesn't give a shit. The air has barely any mass, so it just pushes out of the way. Okay. Whereas internally to the water, you may have some waves. Maybe you have a wave that that travels like this, and it's actually headed to the right, inside of the medium. They can be coupled. We're not talking about them being distinct. And sometimes when you have one form of wave, you have others. Okay? Is there an internal wave that can happen in the air? Yeah, of course, right? So let's say you do have this undulation, goes up and down and up and down. And every time that the air moves up, every time that the water moves up, it pushes the air out of the way. So in fact, it could launch waves, right, off of the water surface. Okay. And finally, what's a compression wave? What do you mean collision? Not quite. That's not how I would think of compression waves. Because waves can go through each other, as long as it's not too dissipative, right? If there's not too much friction, they pass through one another, no problem. This can happen in a single fluid. In fact, it's happening right now.
Then the constraints of the road.
Yeah, it's happening right now. You're doing it. I'm doing it.
Oh.
Maybe. How do you hear me right now? What is sound? Yeah, but what is it? Yeah, how do I make sound? What is it?
Vibrations.
Okay, but we're not in the lattice, right?
That was the atom.
Yeah, so what about the atoms in the air gives you sound? Well, they're not, they're definitely not going from my mouth into your ear, because that would be very weird, right? Okay, there's a whole fluid that we're in, right? You got to put on your I'm in a fluid glasses. You're hearing me because you're in a fluid. In space, no one can hear you scream, right? In fact, the sun is the loudest thing in the solar system. We just can't hear it. There's no medium with which to carry the sound. Sound is a compressive wave. What that means is that when I speak, I press molecules into nearby molecules, and I create both regions of compression and rarefication. And you hear those go up and down as differences in tone and pitch. Okay? So when something comes towards you and it has a high pitch, right? Versus when something goes away from you and it has a low pitch, those are places where the air has been compressed, high pitch, or rarefied, low pitch. And your ear, actually what's in your ear are a bunch of cilia. So these are basically little arms that move around with the wind and they go, oh, I'm getting vibrated, right? And then they tell your brain and your brain interprets it really amazingly, okay? But it's a compression. So unlike these two waves, these are the ones that we traditionally think of, just up and down, you're like, ooh, boom, boom, boom. This is boom, 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 boom. So in fact, I tend to write them like this: compression, rarefaction, compression, rarefaction, compression, rarefaction, compression, rarefaction. You see? The medium is still there. The whole thing is continuous, it's still fluid. But this is an example of a compression wave. Also called a pressure wave.
They say medium or area.
Medium is anything that carries a wave. So we tend to, as long as you're not thinking about light, in order for a wave to propagate, it has to propagate in a medium. Some people call it in a media, right? So waves propagating in media have different speeds. So if, for example, you say step on the ground, hit it really hard, you can actually hear that. So one way that native people would understand where herds of buffalo and bison were, they would put their ear to the ground. Because a large stampede of buffalo will carry through soil, and you can hear in which direction they are and how far away they are. The ground would be the medium, right? Or if I scream, the air is the medium. Now we are very ineffective at communicating underwater. Why is that? Almost. You're correct, but no, why is it that we're ineffective? It's because we didn't evolve underwater, right? So that's not where we're supposed to be, right? We communicate in air, and air doesn't travel well in water, right? So instead, look at whales. Whales can communicate over thousands of miles by using very low waves. How do they do that? How does it sound, right? So think about the way that we communicate right now. I can't shout for a mile, right? And yes, okay, maybe a whale is larger, but is there something about the air versus the water in which waves propagate better in one media than another? The answer is gonna be yes, but we'll see why, right?
So if you were to say it in a sentence, when interface and compression would be waves that are pressed into a medium.
Say that again. So the first part again. So you're saying,
Like to put it in a sentence like we did for interface and internal.
yeah.
What would you say?
So I would just say sound waves. And that's really not the best way to think about it, but that is an internalized way of thinking about it. They're compression waves. So if, for example, you think about an earthquake, one of the things about that's cool about the Earth, we have all these seismometers, we put them all over the Earth. An earthquake happens in Jakarta, and we can watch it propagate over the course of the entire planet. And that is due to surface waves and compression waves. And so we can see those compressive waves move across the planet, right? And that's just where the Earth moves together and then rarefies, moves together and rarefies. In case you didn't think about it already, I say this a lot in my intro astro classes, but in case you haven't taken that with me, of course, when we stand on the surface of the Earth, we are standing on the coldest part of the Earth. As you go down below the surface, it gets hotter. So the interior of the planet is much more liquid than you might think. And even when you start to change your perspective, so if you think not in our human timescales, under which rock is very brittle, but if you think about rock in the timescale of years, millions of years, it acts like a fluid, right? So again, when we think about this quantity that we talked about at the very beginning of the semester, which is how do we define fluids? Well, we said, okay, you have to have a certain number of particles together, and the motion of those particles bumping into each other needs to be less than some other type of quantity, right? On short timescales, rock does not behave that way. On long time scales, it does. Right? And of course, once you melt rock, then of course it's a liquid. Okay. Let's talk a little bit about what the forces are at play here. I kind of gave this one away. What's the forces at play in compression waves? What? No. I do not use gravity to let you hear me. How did I do that? Pressure. My vocal cords go like this, and they go like this very rapidly, and then they press the air towards your ear. Okay. And it also doesn't really make a difference if I go like that or if I go like that, right? Gravity doesn't really care there. I'm gonna have to bounce off the roof in the circumstance where it points up, but a compression wave, most of these doesn't give a shit about gravity. Is that the case for our two other types of waves? Say the interface wave here or here? No. So let's talk first about the interface wave. What are the forces at play here? What do I have to consider when I'm thinking about how do I create this wave? Okay, buoyancy. So are those the same thing or are those different?
You write buoyancy in terms of gravity, right?
You tend to write buoyancy in terms of gravity, right? So the buoyant force is the restoring force, but really we're thinking about the fact that there is some medium that is heavier than another medium, right? And they're going to want to organize themselves such that the more dense medium is below the less dense medium. And those, of course, are two sides of the same coin. So whether you're talking about sinking or rising, that's still gravity. Okay, okay, so there is, for example, this thing goes up, and now the restoring force is gravity pulling it down. Is that correct? Okay. Why does this thing go down? Yeah, so let's say I push this up. Why do I make a hole on the right? Conservation of mass is a very good one. I like that idea, right? Like what we're thinking about there is, okay, I push this stuff up, so therefore I have to draw it from somewhere. What's the physical mechanism by which I can draw fluid?
Mechanism.
Yeah, how can so I push this thing up with my finger or whatever. What? Yeah, I want to drag molecules while I'm doing it. What would I call that? You're almost there. You're like 70% there. What? No. What is the physical like? So we just talked about gravity is the thing that actually pulls you down. So let's say I push you up, and somehow I'm going to grab material. What? Tension. What kind of tension? Surface tension. So these are intermolecular forces grabbing nearby friends, being like, bro, let's go, right? And so as I press this thing up, what happens is this piece here, it could stay flat, but it doesn't. It bends to the will, right? This shape here then takes on the form of the thing that's being pressed up. And then by the time that you let it go, and it comes back down, and it sinks down below, you're also pressing stuff away, and then it presses you back up, and then it presses away, and then it presses. Okay? So some of the forces that we have there are gravity and surface tension, and then we talked about pressure. Okay. For this work, we are going to take a step back and really not going to think about rotational flows. Okay, because we just want to think about waves first in sort of the simplest context, and then we're going to place them all together. Okay, so let's write yeah.
Somehow when we learn about like then sound waves, we know that sound has like a longitudinal wave. Do we not care about that for internal and interface waves?
What do you mean a longitudinal wave?
Like in the direction it propagates, I thought sound has like a more concentrated wave in that direction, but light doesn't.
Okay, yeah, so light is a transverse wave. Those modulations are occurring transverse to the direction that it's traveling. Sound is a compression wave. So it's traveling in the direction of the wave.
So do we not care about that then for interface and internal?
We will see that the interface waves and internal waves, they don't necessarily even need to move left or right,
This all.
right? So that's the really cool thing about a wave, like the ones that we see. Let's just take an interface wave, right? You can have the water doing this and this without it doing this, right? And of course, we'll see the mathematics of that shortly, but for a sound wave, you can't. There's no like standing waves of sound because those are propagating through pressure. Okay. So the technical term for a water wave is a surface capillary wave. They're actually called surface capillary gravity waves, and therefore the word gravity wave is the one that we will use when we think about these surface interactions. You will hear the word gravity waves used in black holes and neutron stars. That is not what we're talking about. Okay, so you're not learning general relativity here. You are learning water waves. Which of these two types of waves, black holes or fluid dynamics, was here first? What? Fluid dynamics, yes. Fluid dynamics is the older field. Gravity waves through general relativity were not predicted until Einstein, or Einstein's theory of relativity, and fluid dynamics has been around much longer. Okay. So sometimes people call them gravitational waves. And that is how we distinguish from gravity, or surface gravity waves, or internal gravity waves, right? Okay, so these are the fluid gravity waves, and I want to start with something, a formalism here. We are basically we're gonna create something like this. Here's a wave. It's called eta. Like a fancy eta. It's just a bunch of marks. Okay. What are the things we need to define a wave motion or a wave itself? Just mathematically. So it is true that those are characteristics that it will have, but how do I mathematically write a wave? Trig, which trig? Okay, so let's use cosine. So I know I need a cosine. What else do I need? An angle of the cosine. You need an argument of the cosine. Good. Okay, what else do I need? An amplitude. Very good. I'm going to use the letter A. Well, let's imagine, I mean, so far we're only in one dimension, so let's not complicate ourselves yet. So we're thinking just about the like what's the easiest way to write a wave? Maybe that's moving to the left, moving to the right. Something in the cosine needs time. Okay, can you help me there?
Remember seeing it like omega t.
Omega t. Okay, I like that. That seems like some shit, right? What? Direction? Yeah, so what would we want to do, like x? Okay, so let's use x, omega t. I'm going to make some clarifications here, okay? So I'm going to start with something like 2 pi. And I'm going to divide it by the wavelength of the wave. Okay, And the reason that I'm doing that is because I'm gonna have some distance x. Now x over lambda, that's gonna give us the right dimensions, right? And then it'll just be like how much of the wave have I created. So that works out, right? And now I'm gonna also include something like CT. Okay? And you're gonna get really mad at me, but I promise it's okay. If C is not the speed of light, C is the speed of
Sound. No. C isn't the speed of light?
well, I'm just saying for this one here. The wave. It's the wave speed. Now, of course, this could be the speed of sound, but generally speaking, as we said before, which came first, fluid dynamics or special relativity? Fluid dynamics. And so therefore, the wave equation, which had a C in it, became the C for electromagnetism. It's okay. We're not mad at them. It's just that it's a shame for you when you're saying, wait, C can only mean the speed of light. No, C means the speed of a wave. And we will see that there are a few different types of speed of the wave. There is something like the propagation speed in the medium. How fast does information travel in the medium? There is the speed of the wave itself, and there's the phase speed in the wave. And we'll define what all of those mean in due time. Okay, let's write a few more things. So C is the speed of the wave. I should really call this phase speed. We'll define that a little bit better later. We'll see this. These definitions tend to work better when you actually confuse them. So something like lambda is what? Wavelength. Okay. And now I can rearrange some of this so that we can make some new fun definitions for all of our friends. So we could say the version that you liked with omega, right? And so if we take 2 pi c divided by lambda, we're going to call that omega. And similarly, 2 pi over lambda, we're going to call 1 over c, or 1 over k. So we could call this thing here a cosine of kx minus omega t, right? Where k here is something new, and it's called the, not quite, because this one has to do with length. It's called the wave number. And it's just basically 1 over the wave. Okay. And similarly, what's omega? Right, but how they AC. Well, because this piece here, gonna cut out. It is what the letters mean, but is there another word for it?
Oh,
Not like speed anymore, right? Because there's no length in the top. It's now the angular velocity is exactly the way that I would think about it, but the word frequency is totally fine, right? So when we think about the wave, omega, right? This is the angular speed. Or you could say the frequency. So some people who really hate me, they say it's the radian frequency. If you said something like the cyclic frequency, which is 1 over the period, that's fine too. I'm not gonna. I sometimes like to police the words we use here, I think in the waves part, maybe it's not so important. Okay. The other rules that we're gonna make here is that we're gonna be in 2D. It's really hard for me to draw 3D on the board. You get it. 2D is enough, right? And we can generalize them. You just add the plus Z, it's straightforward. We're gonna assume some of the forces like the Coriolis force, which occur over very large scales. We're gonna ignore them for now. We'll come back to them when we want to think in terms of like these large scale forces. Geodynamics, which is a section, or I think it's chapter 11, is where chapter 11, 12 is where we'll see them in detail. Okay. So here you go. Waves can move in more than one direction. And all of these properties that I just talked about, they have directionality to them. So you can have X and Y, and we can imagine this is a wave that's propagating in that direction. So the wave propagation direction is going to be a vector called capital K. And capital K has components, okay? The wavelength here is 2 pi over K. That's going to be the wavelength in between here, crest to crest. And you have some length between it that's in the Y direction, and some length between it that's in the X direction, right? So similarly, there is some propagation speed in Y and some propagation speed in X. We haven't done anything new here. All we're saying is that we're going to be a little formal in the way that we describe these properties. So for example, you have wavelength, that's where we start. And of course, you're going to have a different wavelength in X than you would in Y, depending on which direction the wave is propagating. So if the wave is propagating fully in the direction of X, what is the wavelength in Y? Take this wave, take K, place it along X. What is the wavelength here in Y? What? What do you mean 1? Remember that the wavelength is the distance between crests. As I tilt this over, and I move it this way, the wavelength in X is not what I'm talking about. It's the wavelength in Y. 0. The wavelength in Y does not exist, but the wave is propagating only in X. And as I move it all the way up to here, and it's only propagating in Y, what is the wavelength in X? There we go. Okay, so we see the same formalism we thought about before. Let's say I have a wave that's propagating in a certain direction. Depending on how I orient, I can still describe that same wave as components in these different directions. Okay, so I haven't invented anything new, right? Okay. Okay. Let's describe linear liquid surface gravity. This. Okay. So you have some fluid. Okay, this down here is the zero surface, and it has some distance minus h from what I'm going to call here 0 line is sort of the surface at rest. So up here you have some medium, call it air, or even call it vacuum, I don't care. Down here is the medium that you care about, that is your fluid. And what you want to do is you want to begin to understand this process of a liquid surface gravity wave. Okay. Now, what do I mean by that? Where is the liquid? What? Yeah, I would call it the middle of this picture. This here is the liquid. Where is the surface? What? Yeah, okay, let's just draw this distinction, all right? It is not the bottom here that I care about. This is a surface. This is a solid. That's not the one I care about. I care about this surface. This is the surface under which I believe there will be a wave. And the reason for that is we're going to create one. We are going to create a small amplitude, and we're going to ask how it propagates. Okay? We happy? Okay. So we're going to make a couple assumptions here. Maybe I'll pull this up. We have time, right? Okay. So let us begin. On the left-hand side, okay, we're just going to redraw the picture just very small now. Okay. So this is 0. This is A. And also eta. Just like we saw before. This is the surface. This is H. Okay, going in that direction. And this is Z. Everyone happy? This is X. X and Z. 2D. Y doesn't exist anymore. Okay. So let's limit these to small slopes. Okay. So what that means is that A divided by lambda is going to be much, much less than 1. Okay. So that means that they're going to be big compared to how tall they are. And that will allow us to do something called linearization. So this is a mathematical technique by which we're going to look at a series of perturbations. We're going to take the first order perturbation. That first order perturbation is only valid in regimes where the perturbation is small. If you have a large perturbation, and we'll talk about this in detail when we start seeing it, we're going to make some approximations, and those approximations will be totally invalid if A is on the wavelength, say size or the size of the wavelength, right? Okay. Similarly, we also need to say that A divided by H is less than 1. Okay. And the reason for that is that I don't want to have any interaction between the top of my wave and the surface down below. Okay. Okay. For this one, I also said that the flow was irrotational. So how do I define irrotational? Vorticity 0, right? Okay. So if the vorticity is 0, then that means that I can define a velocity potential. Such that phi of x, z, comma, t defines u and z, or I should say w. So this gives us u is equal to del x of phi, and w is del phi del z. You familiar with this again? Okay. That wasn't so bad. Let's really start cooking now. So we have something like an incompressibility continuity equation. Remember that? And that is going to be that the incompressibility continuity equation, which says that du dx plus dw dz is 0. So another way of writing that, this would be del dot u. If it's incompressible, that's by definition 0. So you'll recall earlier on, we would make that simplification. We would say we can call this thing incompressible if this is true. So this fluid then is irrotational, incompressible, and has just a little perturbation. Okay, so we're making it nice and simple so that we can solve these equations. So if that's the case, then it must certainly be the case that we have something like the Laplacian here, del squared del x squared of psi, or sorry, of phi plus del squared del z squared of phi must also be 0. Very good. Good. Okay. And now we have two boundary conditions, and they're fairly straightforward. At the bottom, at the very bottom, where z equals h, and I'm going to write this like this, boundary conditions at z equals h, particularly minus h, omega equals, or sorry, w equals 0. It has to equal 0 at the surface. So therefore, I can also write that since this is w and this is w, that this is del phi del z, that must also equal 0, right? Okay. We're happy with that? Okay, we can also use what's called a kinematic boundary condition. Okay. That essentially looks at the fluid particle velocity in relationship to the normal of the surface itself. And that one's pretty straightforward. So this free surface, this thing here, we're calling eta. It's the location along all of x at which the surface is up and down. So we can say something like the kinematic boundary condition is n, the normal, dotted into the velocity evaluated at z equals eta. Okay. And that is just basically going to be equal to the velocity of the surface itself, n dot u of the surface. This is pedantic. You can write that down if you want. This is in the textbook. You haven't learned anything new yet. Okay. So the place where it does start to get fun is that we can now write the equation of the surface, right? So any location on the surface as f, let's write this in. So the location of the surface is f of x of z of t has to be equal to z minus eta of x of t. Okay, and that thing equals 0. Okay, so what are we saying? We're essentially saying that there is some free surface here, and the free surface is just written in terms of x, right? So at every location x, you have some free surface height, and the difference between the height of the fluid and the height of the free surface must be the same. That's the definition. Okay, and then in that perspective here, we're gonna see that the normal is moving along the free surface as we defined it to. The velocity of the surface at any location is going to be purely vertical. When we write it this way. So we can say something like U of S is equal to d eta dt in the z direction. Okay. Weird what we're doing here. Okay, how do we define the surface normal? Well, this is a little annoying. Here's the surface normal. We're gonna define this as some gradient of the free surface divided by the magnitude of the gradient of the free surface. Okay. And if you want to follow that on home, you can see it in the book, but I'll just rewrite it here very quickly. It's just going to be the gradient of f. So the first one here, right? The gradient of z is 1 in the direction of z, right? So I could write that, I'm going to put it second because z is going to be second. And then the gradient of this thing is just this thing in the direction of x, d eta dx in the direction of x, right? Plus z hat. You see how that's that? Yeah, this thing is this thing. Okay. All right, and similarly on the bottom, we can take the magnitude of that thing. So what we'll do is we will dot it with itself. So I'm going to get 2 versions of this. I'm going to get a version of that. 1 times 1 is 1. And this thing is squared. And then I'm going to take the square root of the whole thing. That'll be eta over dx. 180 squared plus 1. Okay. Okay, so now we have these things here. So we define n, we define u as, and we can evaluate u. So u at every single point. I guess I should have written that somewhere. Let's just use that over here. So u, for example, the vector itself is little u in the x hat direction plus w in the z hat direction. That's the 2 directions that we have, right? Okay. So let's take this thing, okay? And we're going to use the gradient of f here to evaluate del f dotted into u at z equals eta. And that must be del f dotted into s, right? That's what we said here. Magnitude on both sides. These things are related. These comes to the other side. They cancel out. Everyone's having a good time. Okay. So now for the first time, we can begin to think about what is the eta? What are the conditions on eta given this and given this? Okay. So the first part that we have to ask here is that when we do this on the right-hand side, we get minus u del eta del x plus, oops, that's not a plus, plus w. Okay. And that's gonna be equals to del eta del t. Now, if we want to write this not in terms of U's and W's, but in terms of phi, as we did before, we can also write it as this thing, right? Is going to be our del eta del t plus, and I'm going to use the product rule here, del eta del x del phi del x evaluated at z equals eta. That's going to be equal to del phi del x. Okay. Also about. Okay. So that's a long-winded way to say that the top and the bottom right are essentially the same for small perturbations. Okay. So for small slopes, these two are equivalent. Which allows us to write that d eta dt is approximately equal to d phi dz. Evaluated at, I should be a little more careful. Evaluated at z equals eta. Okay. And I know how much everyone loves Taylor expansions, right? We love Taylor expansions. So really what we want to do when we think about any sort of wave expansion or perturbation theory is let's take some small deviation away from, say, flat. And what we're going to do is we're going to imagine some linear perturbation to the waveform. And we'll say, let's break it down in a Taylor expansion. So let's take this thing here. Let's take this thing. I'm going to write it in terms of the Taylor expansion. Let's write this in terms of del z. But let's do z evaluated at 0. Plus eta del squared phi del z squared evaluated at 0. Plus dot 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 dot. That is going to be equal to del. Okay. And basically all you're going to do there is you're going to say, well, as long as this condition is true, this one here, as long as you have some small perturbation compared to the wavelength, then the rest of these terms don't really matter. And your expansion around eta is essentially the same as your expansion around 0. Your free surface is basically following the 0 line to the first approximation. You're waving your hand, okay? And you're just saying this again. You're just saying del phi del z is del eta del t. Okay. We're basically there because once you've done that, you can now write your equations. So you could start with something like a pressure boundary condition, And you can say like at the surface of this, the pressure of the water has to be 0. So you could say something like P. Look at how much I'm actually good at this today. I like left space on the board for the things that I needed later. I didn't even practice. Okay. P evaluated at eta must be 0. That's exactly right. Okay. And that just means that the pressure's got to disappear at the surface, right? So if that's the case, then we can use the Bernoulli equation because we got an irrotational, we got a incompressible fluid. So let's go ahead and write that in terms of the Bernoulli equation for this surface. And this is basically going to lead to I think perfect space. I should have put this up here and that would give me a little hole. Okay. Okay, so let's write it down here. Del phi del t plus E over rho plus GZ equals approximately 0. Okay. So what this means is that we are evaluating this free surface, and if you recall from the original Bernoulli equation, you have this thing inside brackets, and you say that that thing is equal to a constant. Okay, we can set that constant to be whatever we want, as long as we evaluate it far enough away, such that the pressures give you that constant. So we set that constant to 0. So this is the equation for, remember that d phi dt, that's going to be your motion of this free surface. P over rho, that's the term that considers the pressure forces, and then the restoring force of gravity. So this is a competition between gravity, pressure, and the free surface's height with time. Okay. Okay, sorry, we didn't actually get to the wave part of this wave, but this is the math that we need, and we're basically just going to use this to immediately begin to solve the wave height. You may not be surprised to find that it will follow a sinusoidal form. Oh, wave looks like a sinusoid. What is interesting and what we do hope to do is to figure out how do waves propagate in the medium. That is to say, based on whatever conditions are in the fluid itself, the fluid properties, such as how high is H, how big is A, how big is lambda, do these waves maintain or do they disperse? Do they break up? Do they propagate linearly, etc.? Right? Those are the questions that we want to ask ourselves. How do we create rogue waves? How do we get waves that dissipate? Okay. Tidal waves, how do they work? Right? Tidal waves occur when there's an earthquake far away, and they show up in, Singapore. Questions, comments, concerns? Sorry that I went long today. It's fun though, right? Sometimes a little too math, but not too much.